All right, so this is the most important Windows project. I might as well try this one. It is this one here, ED308. And like I said, this is exactly the same thing we just did on Linux, a basic buffer overflow, and how to do it on Windows. So you have to have a Windows running Intel and then a Linux machine on the same network to run the script. And so I've got both of those in the private cloud. I turned off data execution prevention, although I don't have to. It's automatically turned off for client machines of Windows. Client versions have this turned off because it breaks legacy software. And a lot of people run on old things on client machines. Server machines, it's turned on by default because they really don't expect you to run old crap on servers. And by the way, that's a really bad idea to run old crap on servers, like what we're about to do here. This is why. So, and they turn off the firewall, and you can enable error reporting. It's not necessary, but that makes it more interesting when it crashes. And I did all that. And so then you have to run this vulnerable program called vuln server, which is a cool open source program a guy wrote just to demonstrate a whole bunch of vulnerabilities. And it's already on the machine. You don't have to download it. It's in the, if you're using my machine, it's in the tools folder. So I'm going to run that. I opened the tools folder here, and in this mess is vuln server. It's alphabetical, so down at the bottom. Oh, I guess, okay, for some reason there's another tools folder. This is the one, C tools is the one I want. And there it is, vulnserver.exe. So you run this, and it starts listening on port 9999 for incoming connections, and it's vulnerable. It's sort of like an email server. And so you need the IP address, so I'm going to open another terminal. Oh, there is already another open one. Okay, good. Okay, so there's my IP address, 192.168.3.107. So I should be able to come in from Linux. I can do netcat 192.168.3.107 on port 9999. And there we go. Welcome to vulnerable server. I'm in communication with the server. If I give it help, it will show me there's a bunch of commands, and these don't really mean anything, but they're just commands with parameters that look sort of like email server commands, and these all have various vulnerabilities. All right, so I've proven it works. So now we're going to have to put some code on there, and probably the easiest thing to do is to open the instructions on this Linux machine so I can copy and paste inside the machine. So let me get some of this going. All right, here comes the Firefox. This is good. Oh, hopefully I'll have internet on this one. The other one didn't like me opening the internet on it, which is weird. Sam's class, come on. Okay, good. Looks like the internet's working. That's good. Oh, good. There we go. All right. So this is the exploit development. And this one here, ED308. All right, I'm just trying to get the code for the Python. All right, here we are. All this jazz is done. Yep. All right, now I'll make the fuzzer, and it looks like that. All right, and I want to put that here, so there we are. All right, so I can, I'll make a directory ED308 and go in there, and then nano fuzzer.py. All right, paste in that stuff, and the only thing I need to fix is the address of the server. So that's 192.168.3.7, I think. There. And so this opens a TCP socket to the server, and it just sends a length of an attack, and it is trun is the particular server command for attacking, because that has a simple buffer overflow. And then you're supposed to put trun and then a dot and then a whole bunch of A's and then carriage return line feed. And this B means byte string, which in Python 3, which is the right way to do it. And then you just send that to the server and print whatever comes back with receiving. And then it's done, and then it just exits. That's all this program does. So I save this, and then I run it. I think just Python. Fuzz might be Python 3, we'll see. Maybe Python 3. There we go. So length of attack 10. Okay, it didn't connect. Maybe I put in the wrong address. The server is 3107. Well, good. I'm glad you caught it. Let's see. You got to get back to editing my server. 3107. Oh, you're right. Thank you. Good. Good. Well, that's understandable then. All right, so let's try running it again. If I put in a length of 10, it works. It says complete and goodbye. Okay. And let's, by the way, make this visible so we can see the window that's listed. Okay, so there's my server listening. Here's my Linux machine attacking. So let's send some more, like 1,000. And that's fine too. So let's send 2,000. And now it crashes. And here's the error reporting telling you it has stopped working. So there's a crash at 2,000. All right, and if you, that's one thing to know, so I'm going to restart it. Okay, and then if I go here, there's also a crash at 3,000, as you might expect. Okay, and it turns out they are not the same. Okay, so I'm going to stop this, and now I'm going to restart the server again, close program, restart it. Okay, and what I'm going to do is run it in a debugger. That's what we did before. We have to analyze the crash. So I start the immunity debugger here. It's just a graphical Windows debugger that does the same thing GDB does, but it's prettier. And so now I open the program in here, File, Open, and it is C Tools. Nope, okay. Pressing T didn't help. C. There we are, Tools. There it is. Okay. Now, we adjust the appearance here, so that's less crazy. It is kind of a process. Okay, it's appearance, fonts, all. OEM fixed font is good. And then I can fix that by going into Options, Appearance, Fonts, OEM fixed, change, and I can make it bigger. I'm going to make it, there, Lucida, bold, 14 would be pretty good. And then OK. And OK, all right, now we can actually see things a little better here. So this is the way the debugger looks. On the left, you see the current code. By the way, the most important thing is always at the bottom and the right. There's a real simple reason. Whenever you have a complicated program like this, the main pane is for expert information. The stuff for beginners is always shoved to the right and the bottom. So the most important fact is down here, paused. The program is not running. This is the number one mistake. You start at the debugger, then you try to send traffic to it, because when you run a debugger program, it launches it and stops, because it assumes you want to examine the operation. So it's not listening right now, not until you run it. The next thing is here is the source code. Now this is the assembly code that's currently running, and actually the easy part of the assembly code is shoved over to the right. On the right you'll see little system calls here, and we'll do a lot of this tomorrow in malware analysis. You don't even have to read the assembly often. You can just look for the C library calls and kind of get an idea of what it's doing, and those are shoved over here to the right. But if you want to read assembly code, you've got it here. You've got not only the assembly code, you've also got the addresses, and the raw hex of the assembly code. And so that's the assembly code that could be running. Over here are the registers, the ones you talked about before, the instruction pointer, which is the next command be executed, the base pointer and the stack pointer and other registers are right there. This is the stack. And the stack mostly contains return addresses. First you have Windows, then you call some Windows component that calls another component, that calls another, that launches your main program, and then it calls subroutines, and this is the list of addresses that it's going to use to return from all that. So these various return pointers are in there. And this is just an area where you can dump any area of memory in hex and ASCII to see what's there, just like you would in Wireshark. And I'd expand these windows if I could get a hand on. Yeah, I'd grab them and make them a little bit bigger, because when I made the font bigger, the default width is not enough. There we go. All right, so that's getting familiar with the debugger. So now I want to run the program, so I just hit the run button here. Now it's running, so now it's listening. So now I can fuzz it. So if I run the fuzzer again, and I send it 2000, it crashes, and now it tells me what happened down here. Access violation when writing to 41, 41, 41, and 41. So this is like the format string vulnerability. I have an opportunity to write somewhere. That's nice, but that's not easy to exploit. So let's see if the other one is better. You do debug, restart, and then, yes, I really want to restart it. It reloads, but it's not running. You have to run it with the run button. Now it's running. Now I can try sending it the 3000 length attack. Now it crashes, and this time access violation when executing 41, 41, 41, 41. So this is the easier one to exploit. This one I get direct control of the instruction pointer. So that's why I say always keep the length the same, because a different length would hit a different bad line of code. I want to keep hitting exactly this bug because I can exploit it. And not only that, I'm pretty sure in the last 1,000 A's, one of them is got in, because the first 2,000 didn't get in. So now you just have to make a non-repeating exploit, and I think I'll just talk about the rest of this. It's easier than demonstrating it there. So you find that there's a crash at 3,000 that's exploitable, and now, all right. And there's a flag defined there, it doesn't matter. Send 3,000, we're fine, you've done all this. So now you just make a non-repeating pattern of characters. And so I just made a series of loops in Python that will create a 3-digit number and then an A. And so you have this, it creates a pattern like this, 001A, 001A, 002A, 003A, and that's 2,000 long, so I put 1,000 characters and then this mess and feed it up there. So you make Python that sends that up. This will send up 1,000 A's and then this 2,000 characters of non-repeating. And when it crashes, it'll tell you access violation executing this. This is 1A25. And that appears here in the code, 1A25. So now I know how far in, and it turns out that that is, I think, 2006 bytes in. And by the way, it depends on which version of Windows you're running. That varies by a little. So this is the right one, I think, for Windows 11, so it'll probably be right today, but as the years go, people run on a different server version and everything. So you have to find the right point. And so now you can target the EIP precisely. You can make your attacks as 2006 A's, then BCDE, then enough F's to get a total length of 3,000. And if you got it right, you'll get the BCDE in the instruction pointer. And this one's right, so when you crash it, it'll tell you BCDE. 42 is B, 43 is C, and so on. And if you see anything else, then you know you got it wrong. If you see A's, you got to move to the left. If you see F's, you got to move to the right. You know, that's why I always do it with trial and error, because trying to figure it out is too hard. There are very often little adjustments that are hard to figure out. So now I know how to control the instruction pointer. Now I need to figure out how to run some code. And you cannot turn off address space layout randomization in Windows. So you can't put in a fixed absolute address. It'll be moving. But you don't need to, it turns out, because if you go to the crash here, and then you look at ESP, the stack pointer is pointing somewhere, and if you just look at the memory at that location, you can right-click the stack pointer and follow in dump, and that will dump it down here. And when you do that, you'll see a bunch of F's. At the point of the crash, the stack pointer is pointing to some of the code you injected. So you already have a point to get to it if you can If you can jump ESP, you can reach the code you've injected even though you don't know where it is. And in fact, if you scroll back a little, you'll find it's right where the F's start. So you don't need to find where your injected data is. You just need to find a jump ESP instruction somewhere that's not going to move. And that's a pretty common instruction, and that's what Mona does. Mona is a plugin for the immunity debugger. It has you can write Python scripts and add them, and it's a pen testing tool they've added. So what you do, there's a separate test for bad characters to find out which characters are not permitted. And then you can put in Mona. Mona's already installed in my machine. And then Mona will tell you about the modules. You can execute Mona modules, and it will show you all the loaded modules and what security measures they have. So here is Windows features, and see, for example, here's address space layout randomization, and you can see there are things that do not have it turned on, and that's what you need. And the two that don't have it turned on are Vuln server itself and ESS func, which is why you don't run old crap on your server. These compiled with old compiler switches, and if you don't compile it with the right switch, it does not have the ability to be relocated in memory. When you compile it, it has to add an extra section called a reloc section, which tells it all the hard-coded addresses that have to be fixed when you move it. And if it's compiled for compiled for Windows XP, that switch didn't exist. So if you run old XP-based code, it'll run, but it makes your server vulnerable. And that's what happened here. Now, so you can use Vuln server itself, but the problem with Vuln server itself is the main executable always loads at a virtual address of 400,000. So the addresses all have null bytes in them. So you can't use them. If you try to put them in, they'll break your string. But the library called sfunc.dil is loaded at 6250,000. So there are addresses in there that don't have null bytes, and it doesn't move. So all you have to do is find a jump ESP instruction in that module, and Mona can do that for you. So you go down here and find jump ESP. There's the command, Mona find the command jump ESP in this module. And it turns out that there's 9 jump ESPs in that module. Every one of them will do. It's an address that never moves, that will jump back to the stack pointer. So you just take the first one, 6250 11AF, doesn't contain any null bytes. Now you know what address to inject. So you can build the exploit. Here's the exploit, 6250 11AF. You have to have 2006 A's before it. Then you have a NOP sled and a break and padding. This is the prototype exploit. And so you can run it and see that it works, and it is pretty cool. So you run it, and this, by the way, is the test for data execution prevention. If data execution prevention is active, then even I injected letters and they've gone on the stack and they'll go, but when I run them, they won't run because execution is prevented. But we checked earlier on, and DEP is not turned on client machines. It's only turned on for essential parts of Windows. Software apps you added do not get DEP protection. So since this is a software product I added, Vuln server, it doesn't, and that's the point of this test. This test loads in memory a bunch of NOPs, and then the increment, NOP, and then the break, and it made it through the NOPs and hit the break. If data execution prevention is turned on, you cannot even execute a NOP. It'll hit it and then say, nope, can't execute it. So that proves I have execution, and now you just have to put in the same old attack code that you get from Metasploit, except you use a Windows attack. Use Metasploit to write Windows Python code for a Windows attack, and this I'm doing the reverse TCP, what we should have been using all along, where it's going to deliberately call to my home server, which is your Linux machine. And so you get the code here, copy it and put it in your exploit. It's going to look like this. You connect to your server. You have a NOP sled of 16 bytes. You have a prefix of 2006. Here's the address to jump NOP. Here's all the Metasploit generated code. And you have to run a listener on a Linux machine. This is the way Metasploit works. If you start a Metasploit reverse shell, you have to have a Metasploit listener to receive it. So you start that on your Linux machine, run the exploit, and you will get a remote shell on your Windows machine. It's the whole process. It's good to go through. Same thing we did on Linux. It looks a little different on Windows, and it does show how to overcome address space layout randomization. So that's the game, and you can then play some games here. This is what you can do on a Windows machine. If you can get system, this is surprising to me. Escalating from a non-system user to system privileges is supposed to be difficult. That's the whole point of local users. But Metasploit has built-in modules that just try like 4 tricks that are years old, and they just keep working. I don't know why Microsoft doesn't patch them. Microsoft is strange. But anyway, so you just try get system, and it will probably work. And once you're system, you can steal the password hashes. Like we were cracking them the first day. That's how you get them. You get system, and then you can run LSA dump SAM, or a variety of commands that will dump the secrets off the machine, and you'll get password hashes. And then you can just feed them in Hashcat and crack them, or Google them, and so on. So it's a good one, shows you those tricks. But you do need a Windows machine running on an Intel processor. The only reason, by the way, the only part of this that won't run on Intel is the Metasploit shellcode. Metasploit doesn't seem to have the ability to make native ARM attacks yet. I think it will pretty soon.
Wait, what? No, yes it can. Oh, on Windows.
On Windows, yeah. Even on Linux, I haven't had it making good shellcode that works.
I have.
Yeah, oh wait, I remember the problem. No, the problem is Vuln server is not compiled for ARM. So it's running in like a translation library if you run it on Windows, and then the shellcode won't run. Anyway, I haven't found a way to make it work. So as far as I know, this will probably be overcome eventually. I've been trying for a while, and pretty soon I'll be able, probably I need to recompile Vuln server for ARM, and then, anyway, I think once it's stuck in the emulation mode, you can't get back. But anyway, I've tried and I haven't got it working yet. You might be able to get it working. I agree with her, it's probably possible, and I spent a long time trying to get it. I didn't quite get it working. So right now, you need to be on Intel, but you know. Anyway, give it a shot. It's fun on Intel, and it's a challenge on ARM. You probably could do it on ARM. Vuln server is public source code. You could compile it for ARM, although I don't know if you can find a version of Visual Studio that will compile to ARM, which is what you'd need, but it's probably out there. Anyway, maybe Caitlin will have it solved by tomorrow. Anyway, but I don't have it working that way yet. So give it a shot. And like I say, that is the other most important